You have learned your first bits of information about variables and types when you learned about the type integer. Integers are a type in C#. When we create a variable with int counter, what we are doing is creating a variable called counter of the type integer. Types are various forms of data that can exist in C# in specific structures with specific limits. Variables are the names given in code to access and manipulate data at a set location of a specific type. So when we say int counter, int is the type and counter is the variable. Beyond integers in C#, there are a whole host of different types that can hold different styles of data with different ranges and limits. Now let's speed things up a little bit and dive into a whole host of different types in C#. There are two kinds of types in C#. They are called value types and reference types. Value types, like integers, store their data, such as the number 5, directly. Reference types, on the other hand, as the name suggests, store references to their data. The best way to think of reference types, as we will cover these in future lessons, is like this. A value type is a text file on the computer. You open it, edit it, and save it. The text you wrote is saved in that file. A reference type, on the other hand, is like a shortcut to a file. You can have multiple copies of a shortcut that all point to the same file. However, accessing the data by opening the shortcut doesn't open the shortcut itself, it opens the original data file. It simply finds the source file and opens it. Any edits you make are saved to the original file, not the shortcut. Deleting the shortcut only deletes the shortcut and not the original file. Rewording that sentence now to read with references in mind, you can have multiple reference types that all point to the same value type. However, accessing the data inside a reference type doesn't edit data stored in the reference type itself. Editing the data accessed by the reference type edits the data stored in the original value type. Don't worry too much about reference types for now, we will cover those in a future lesson. This lesson we will focus on value types. When choosing to store some data in your application, it is important to store data as the right type to make it easy and efficient to work with. There are only a handful of types that make up the majority of all other types. I'm going to cover all these simple types now. The important details you need to know for each type is the range of possible values, and to a lesser extent the size they consume in memory. So here we go, let's create a variable of each simple type. The above are all called integral types, simply meaning they hold whole numbers. The only difference is the min and max values they can hold. If we did not care about memory on the machine, you could simply use long and ulong for every type that represents a whole number. However, that's not the world we live in. We care about our memory. The size of these types is in order, smallest to largest, and the range of the values is as follows. Where do these limits come from? They come from the size in memory that the type takes up. Let's look at this nice table by Microsoft. As you can see, an S-byte type is 8 bits. That means it takes up 8 bits of memory. A bit can be yes or no, 0 or 1. Basically, it's one thing or another. If you combine 2 bits and you try to represent as many possible different values made up of those 2 bits, you get 0 and 0, 0 and 1, 1 and 0, and 1 and 1. Where this is 1 bit, this is the second bit. There's only this many combinations of 0 and 1 in any order and any value that can make up a possible unique value. That means the range of a theoretical 2-bit sized type would have a range of 4. An S-byte is 8 bits, So that is 1, 2, 3, 4, 5, 6, 7, 8 bits. They could be represented like this, then like this, then like this, then like this, and so on. It is easy to calculate the number of possible options that each bit can represent. To do this, we take the number of possible options in the bit, which is 0 or 1, so there's 2 possible options, and then we times this number over and over by the number of bits there are. For example, it would be 2 times 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 2. Or more simply written, 2 to the power of 8. 2 to the power of 8 gives us 256. Now notice S byte has a range of -128 to 127. That is because the S in S byte stands for signed. The sign being the negative symbol representing if the number is positive or negative. When this value is stored in memory, we use one of those 8 bits to represent the negative sign. This leaves us only with 7 bits. 2 to the power of 7 is 128. That gives us the possibility to say we are a negative or positive, and we have 128 different numbers. But don't forget about 0. 2 possible numbers, including 0, would be 0 and 1, not 0, 1 and 2. So 128 possible numbers, if we start with 0, is 0 to 127, not 128. As we don't need to represent 0 twice for both the positive and negative sides, we have that one extra value left to allow us to represent the negative 128. This is why the negative value is 1 further away than the positive, because we have -1 to -128, and then we have 0 to 127 for the positive. Don't worry too much about this, as I will do a separate lesson on it later, but it's good to have some starting knowledge. With the exception of bytes, all other types use the U prefix to explicitly state negative values are not available. U means unsigned, as in there is no sign value, the negative sign. So int is signed, meaning it can have a negative symbol. A uint means unsigned integer, so no negative numbers are allowed. The next question then is, why would we use unsigned? The answer is really for 2 main reasons. 1, to force data validation. If we want to ask how many years someone has been alive, -1 is not valid. So we can force a little bit of type safety in our code by using the unsigned type. We can see here an integer of my age of -1 is allowed, whereas an unsigned integer of my age with -1 gives us a compile time error. If we tried to build this code, we get the error constant value -1 cannot be converted to uint. This prevents our code from even building, thus preventing this kind of error happening long before it gets into a real-world application. Let's also test what happens when we try to give a value, such as a byte, a number greater than what it can possibly store. Notice my byte of 256 gives us an error of constant value 256 cannot be converted to byte. If we change this back to 255, it will happily compile. This is the benefits of C# compared to other languages like JavaScript, for example, that are happy to assign any value of any type, range, or size to any other, and to only find out about your issue when it's time to run your code, whereas with C# we find out about the error while we're writing code. So we have all these ways to represent whole numbers. But what about floating point numbers? those that can represent fractional numbers. There are three kinds of floating point numbers: a float, a double, and a decimal. The main difference being the size, 32 bits, 64-bit, and 128 bits, which also correspond to the accuracy of the digits stored in that number. A float can store approximately 6 to 9 digits of accuracy, a double can store approximately 15 to 17, and a decimal can store approximately 28 to 29 digits. Note that in floating point numbers there are no unsigned specific types, such as UFloat. The reason why there is not is a big rabbit hole of how CPUs work, their instruction sets, and a bunch of maths. I won't be covering that in this lesson as it's of very little importance to know the reason why. Just simply be aware that floating point types cannot be unsigned. This goes for every other language that I am aware of. It isn't a C# specific limitation. It is due to how CPUs are created and their instruction sets are run. Now to look at the accuracy of floating point numbers. Let's see what happens when we output the value of my float given 6 decimal places of accuracy. The F here is how we define a float. If we didn't put the F, the compiler defaults to a double, which will then give us an error saying that the literal type double cannot be converted to float. Now let's run this code and see the output. As we can see, the output is expected 1.000001, which is 6 decimal places. Let's give it a range outside of 6 digits. Let's give it 7 digits. In this case, it's now outputting correctly. Let's give it 8 digits. And now we are only getting 1. That is because it cannot represent the 8th digit in this particular instance. Let's change the last digit to a 6, and let's see what happens. As you can see now, we have 1, 2, 3, 4, 5, 6, 7 digits, even though our value is 8 digits, and what has happened is the 6 has been rounded up to turn this number into 1, 0. More importantly though, notice how there has been no compiler error preventing us from storing a value in the variable where the pieces of information are lost. We have said that my float is 1.000000006. It has not told us of any error, yet if we check what the value is right after, it is not this value, it has been rounded up. We can also lose values inside of the constant portion of the number, which is to the left side of the decimal place. For example, let's write a number such as this. If we see the output now, you can see we are getting scientific notation output. So let me just first fix that. Don't worry about this magic here yet, that will be explained in future lessons. Let's run the code again. And you can see the output we now have is a completely different number than the one we gave. We gave 5111 as the ending numbers. We actually have 4752, a completely different number. And again, the compiler hasn't warned us or told us that this number isn't correct. That is as much depth as I will go into on floating point numbers for now, as they require many lessons of their own. Just be aware of the potential data loss of storing data in high precisions. And the best general advice if you have any high precision floating point numbers is to simply use decimal. I know it's the largest size, but in this case, data accuracy is far more important than memory. Finally, the last 3 most important simple types. Well, one isn't a simple type, but we will cover it. We have a Boolean, a character, and a string. This time, to find out the size of a Boolean, let's do this. This will give us the size of the type in bits. The times 8, which multiplies the result of this expression by 8, is because the size of gives us bytes, not bits. A byte is simply 8 bits, so if we multiply bytes by 8, we get bits. Most computers won't store data in less than chunks of 8 bits, forming bytes. This is again for performance reasons and architecture reasons. The CPU instructions operate typically on bytes. Again, a lesson for another day. For now, just know that all types will be in quantities of bytes, so multiples of 8 bits, as we can see here. 32 bits is 4 bytes. So a float is 4 bytes in size. 64 bits is 8 bytes. So a double is 8 bytes in size. And 128 bits is 16 bytes. So a decimal is 16 bytes in size. So if we now run this command line with a bit of added text for visual output, you will see that it tells us a Boolean is 8 bits. We could add another value here to confirm the size of any other type. For example, let's check the integer type. So if we do size of int, we will get an int is 32 bits. If you wanted to display in bytes, you can remove the times 8, change the text to bytes, and run again. And we get an int is 4 bytes. I will just change that back to a Boolean for now. And you can see a Boolean is 1 byte. So a Boolean is 8 bits or 1 byte. That means 256 possible options, right? As we worked out here. For 8 bits or 1 byte, there is 256 possible options. Well, no. A Boolean is a truth value. It is true or false, yes or no, similar to the bit. It has 2 possible values then. However, as mentioned, due to CPU and performance issues and architectural reasons, a Boolean is simply placed in a byte as it is the smallest sized piece of memory that CPUs want to store. So even though theoretically the Boolean could store 256 values, it does not. It stores true or false. Boolean is named after George Boole, a self-taught mathematician who invented Boolean algebra. George Boole is in some people's eyes the inventor of the modern information age. Without Boolean logic, true or false, transistors would not exist. Transistors form CPUs, CPUs form all your computers, and effectively all of technology as we know it. Without Boolean logic and Boolean algebra, we wouldn't have any screens, computers, radios, or many of the things we have today. You'll use Booleans a lot in code. Anytime you want to represent true or false. For example, are we loading a page? Is a button enabled? Is a feature unlocked? And so on. A character, or char for short, as I pronounce it, is just a U short. So it can store just over 65,500 different values. The character type is used so instead of storing and representing numbers, it can represent Unicode characters. Unicode characters are letters and symbols of our languages, our written words. For example, every letter on the alphabet is a Unicode character and can be represented by a character. We use single quotes followed by any character on your keyboard, and that's how we can initialize a character with a specific Unicode character. A character can only store a single one of these letters or symbols. Placing 2 characters inside will generate the error, too many characters in character literal. And you can see the hint at UTF-16 code in the text there, which refers to the 16 bits size of the character. Finally, a string, which is not actually a simple type, but here because we already use it, and it's very important to know at the start, is a collection or an array of characters. So it can store however many characters it needs. That's well beyond this lesson, but you can think of a string for now as a collection of characters. You can see here we can create a string with double quotes, and we can place as many characters inside of the string as we like, whereas with a character we can only place one. The size of a string depends on the size of its value, and again beyond this lesson, but in this example we have 3 characters, so we should get 3 times 16. There are many more types, such as datetime for representing dates, time spans for representing a span of time, such as 1 hour, and many others. However, those behind the scenes are all made up of these same simple types. For example, let's look at the datetime source code. As you can see, all it is made up of a bunch of longs and ints, both of which we have just covered. That's a lot of information we've covered in one lesson. The main thing I want you to remember is the various options we have for storing information. They are whole numbers, floating point numbers, truth values, which we didn't actually show, such as my bool equals true, or my bool equals false. These are the only 2 possible options of a Boolean. Or text. Pretty much all other types as we go forward are nothing more than collections of these types of values for an easier way to represent more complex data structures. Don't try to memorize them all, and don't try to memorize exact sizes and ranges. That information is useless. Instead, try to remember the approximate sizes, such as a U short is approximately 65,500, and an integer is around 4 billion. One important size that I would expect you to remember the exact values of is a byte. This will become apparent in future lessons, but do remember that a byte is 256 bits of information, and specifically, and that means 0 to 255, not 256, which is a common mistake some people make. We will use these variables as we move forward, and you can keep referencing back to this lesson to get an overview of these simple types. The more we use them, the more each type will become familiar, but this will be a good reference lesson for you to jump back to see how almost all types are created.